And the thing is, the Python library, you have to write like big long strings. Yes, I just know I've been using actually, I think
So I get the sense that as soon as the deadline was extended, people kind of took a little breather from projects. But hopefully there are still questions because we also have 2 midterms this week, so hopefully we didn't blow off Friday yesterday. But what questions do people have? Yeah.
What's the correct syntax to declare a priority queue of points? Because I've been trying and trying, and I'm doing something wrong in my syntax.
Yeah.
Also, I tried to pass the comparator, and I wasn't sure if the top of the queue is going to be the thing that was the least distance away or the greatest distance away.
Yeah.
And I know in the script we talked about getting the farthest point away. And so I wasn't sure if I could my own comparator or like flip it around.
Yeah.
But I couldn't build it to test it, so.
Let's look at the documentation so we can kind of work through this together and see like what the key bits are. Okay. So yeah, kind of start by looking at the documentation. This one's a little bit weird because there's a whole bunch of template parameters. And so we kind of have to look at what they all mean. So T is going to be the type of the elements. So for our case, what is T going to be? It's going to be a point, right? Because that's the the data type that we're working with. Right? We're going to have a priority queue of points. Okay, cool. Container is how we're going to hold them. So the suggestion is to use a vector, which that's what we want, right? So priority queue is just an array that's sorted in a particular way. So we're going to give it a vector to work with. And then the comparator is a type that compares them by. So we see the comparator is defined such that it's true if the first is before the second. So it's basically comparator is a less than type thing. But because priority queue outputs the largest elements first, the elements that come before are actually output last. So basically the front is the biggest element. So if we compare by distance to a point, it's actually going to do exactly what we want. So maybe let's play with that. Godbolt, we've looked at this before with the assembly stuff. It's actually pretty handy for just testing stuff out. So let's just maybe see if we can play with a priority queue. First to get a compile, and I believe that Godbolt lets us run stuff now too. So So we'll just play with that. Yep. So Q. So let's start by trying to declare it. So we want a standard. So maybe let's start with just ints, because just to make things easier. Right? So we'll start with the 30 Q, and then our 3 template parameters are going to be int, vector of int, and then we need a comparator. So maybe we'll do like the 1D version of the distance comparator. So let's add, make a comparator struct, and will be just like a simplified version of the distance comparator. So we'll have like a int x, and then, so we're just gonna, this is like the distance to, or we'll just do the distance to this point x. So our operator equals, or operator parens. We'll just see which one is closer. So this is like just the 1D version of the distance from point comparator. And we're just going to see whether A is closer to X or B is closer to X. Cool. So does everybody see how this like translates pretty close to what we're doing with the points? Okay. All right, cool. So we have kind of a simplified example here, right? And then here we need to pass a comparator, or we need to we didn't specify the comparator. We're going to, the type that we're doing here is a comp, and then the actual parameters we're going to pass are, look at the constructors, there's a lot of them, but so probably the one that we want is we'll pass the comparator, because we're starting with an empty priority queue, and that's kind of the only thing that we need to provide. Does that make sense? Okay. So we'll just pass a comparator. Let's say we'll measure points, how far points are away from 5, and then we'll just see how things go. So the other methods, so we'll do push. So we'll just loop through the numbers from 0 to 10. Out here, and then we'll just pop them all out and see what order we get. Cool. So we'll just do all while we're not empty. Oh, looks like pop is actually void, so we actually need to do, that's a 2-step thing. You need to look at the top and then pop it. Cool. Everybody, does that kind of make sense how we're doing this? So I think we'll actually be able to simplify this in a second, but let's just make sure that this compiles. forgot a couple things. Please tell me why it failed.
Just can you vector.
Oh. Cool. So it does compile. And this one. I will. I'll post this code. So I think we can simplify this this declaration here, because the compiler can figure out what some of this stuff should be based on the types we give it. So it knows the type of the comparator we're passing. We actually don't need to tell it. So it should still compile. Yeah, well, maybe that is necessary. I'm pretty sure we could get rid of some of these template parameters and let the compiler figure it out. But we can spell them all out here because we know what they all are. Is that?
Yeah, I haven't realized once you name it, you still have to pass the comparator again.
Yeah, so this is here, we're just saying what the type is, and here we're giving it a comparator that, is actually going to compare against a particular point.
This is unrelated, but the use of auto in your loop, does that have any kind of performance impact, or is that just repeats it?
No, so at compile time, it'll figure out what it would be. So the only performance thing is if I put a different type here than what these were, the auto avoids a conversion. So auto will never make it slower, but it could make it faster if you mismatch types otherwise. Cool. Is that helpful? Another thing, looked like there was some template ugliness with the recursive functions for the searches. So I would actually recommend making the recurse functions be member methods of your node class, and that'll make things a little bit easier. So you'll have access to the split dimension part of your node, which should make things a little bit easier. So yeah, I would just make those methods of your node class. Another question?
For the KNN function in my KD tree, we talked about looking at the closest, the distance from the point to the closest point in the region on the left and right bounds, and it's less than the distance from the point to the higher point in the neighbors you already have, right? What's I have a hard time figuring out how to determine what the closest point in that region is.
I think I gave you a function that takes an A, B, B, and a point and gives you that. But really all it does is it just clamps the point that you give it to the AABB that you give it. So it just, if the point is outside of that range, any dimension, it just clamps it to the closest endpoint. So I think, I'm pretty sure I gave you closest point in box or something. Closest in box. Closest in box.
Cool.
Yep. Yeah, if you look at the implementation, it's just clamps in each dimension. Yeah.
We get a little bit of help from instance of our code for getting the quad tree the structure, you know.
Yeah, sure. So, um, let's talk about what's in here. So we talked about there was kind of two different types of quadtree node that we could have, right? So if I were to draw this as an actual tree, it would look something kind of like that. So actually, the nodes in here kind of behave a little bit differently. They're stored different information depending on where they are in the tree. So what were the kind of the two general classes of nodes that we have? So is this node going to store any points in it? No. But what about this node? Yeah, probably. So our quad tree, right? The leaf nodes, right? The ones at the bottom are going to have basically an array of points, and the internal nodes are going to have children. Yeah. So we could do like some sort of inheritance stuff to have a node class and then have a leaf node inherit from that and an internal node inherit from that. I generally don't like inheritance, so I would just throw down a Boolean to tell you, is it a leaf or is it an internal node, and then just have all of the data that you would have for either inside of here. Okay. So we're going to waste a little bit of space, but really not that much. Cool. All right.
So I made the inner node. They also have points. So like for the root and the root node, all the points in this picture.
Oh, I see. So that you could do that. That's going to use a lot more space, right? Because we're basically duplicating most of the points a bunch of times. It probably isn't going to help you that much in any of the operations we're doing, because when we're doing the queries, I don't think we're ever going to be looking at those lists. So for some applications, that might be a helpful thing. For the types of queries that we're doing, I think it's probably it probably won't have any significant impact. It'll just use more memory.
I guess I don't really see why that meant the non-inheriting type would use more memory. Is it a Boolean?
So
you can just leave everything null if you're not using it. Right?
Yes. So let's talk about what else is in here, and we'll see why it makes a difference. Okay. So let's assume we are a leaf node. What's in here? And so for a leaf node, we have vector points. Okay. What if we're an internal node? We need basically a unique pointer node for like the southeast, southwest, northeast, northwest. So we have 4. We're going to have 4 children, right? You could, you can label them however you want. I'm using, geographic directions. Use whatever you want. Right. And so the reason this is using more memory is because I'm storing 4 pointers here, and basically a vector is basically 3 pointers. So I'm storing at least 3 more pointers that I need in each node, which for this application, I don't think it's a big deal. Right? If you had a really huge data set, you'd want to store, a leaf or an internal node. You would only want to store this. A leaf node, you'd only want to store this. But for us, it doesn't really matter. The other thing that might be useful here is to store the AABB for the node, because when you're recursing either to look at the children or to make your children nodes, or like deciding where to search, right? So you'd want to know, like, you need to know where the middle of your node is, so you can split it into 4 quadrants. So I'd store the AABB in here as well. Yeah.
You said this data structure is all TBD, right?
Mm-hmm. So the tricky thing here is like, so iterating through like a range of buckets when we didn't really know the dimension ahead of time was a real pain. Having 2 to the number of dimensions children that you somehow split on and do all that stuff when you don't know the dimension ahead of time is an even bigger pain. So yeah, like if you were going to do an oct tree in 3D, you'd probably just write a quad tree and an oct tree separately, as opposed to trying to do something generic. Does that help?
Yeah, can we kind of go over the inner node, how that's kind of set up?
Like how we construct it, or?
Yeah, what we're...
Yeah. So maybe let's just talk about the node constructor. So we'll just take, the range of points that we want to construct this node with. So we said there's like a limit, right? Like a size limit for how many points we could, like how big a leaf could be. We call it like max leaf size. So if we're under that, then we just want to make a leaf node, and that's really easy, right? So if so how do I get the number of points I'm looking at for this node? Yeah, so just do n minus begin. And so this is less than the max leaf size. And it's a leaf. And points is just going to be a vector with these points. So that's pretty. The leaf case is pretty easy. And if it's small, I just make a vector out of the points. That's good. Otherwise. I have too many points for this to just be a leaf node. I need to split it up. Right, so how am I gonna? What do I have to do if it's going to be an internal node? I have to split it into 4 pieces. Okay. So here the function that would be pretty helpful is standard partition. easier thing would just be to make 4 vectors and just loop through other points. So either of those is totally reasonable, right? But we're going to make, somehow we're going to split up our data into 4 pieces by comparing it to like the middle of our box and seeing is the x less than 0 is the y, or is the x on the left half is the y on the top half, whatever. Splitting it into 4 pieces, and then just setting the children and calling the constructor on the children. So basically here I'm going to split into the 4 pieces and then call the constructor for my children. Again, I kind of left out dealing with the AABB, but you probably want that to be part of it, so you might maybe have a few more parameters passed in here. Other questions on the homework? All right. So the plan for this week, we're going to do midterm review today. Tomorrow we will talk a little bit about NLP, natural language processing. It is a massive, massive, massive field. We're going to just barely scratch the surface about it and talk about some of the key ideas of modern NLP, which is basically we take language and then we try to turn it into points and vectors, and then we use one of the classification or whatever tools that we've talked about on it. So we'll talk about some strategies there, but basically, I don't know, maybe old NLP we're hand building these really complicated models of how language works, and with a lot of really deep domain knowledge about the rules of language and all that stuff. And now we just here's this huge dump of text. We do something kind of smart to turn that into vectors, and then we run KNN on it or something. So that's kind of the gist of what we'll talk about tomorrow. Is just kind of some of the basic NLP tools that we have in our toolbox, and then how we can transform a big, a bunch of textbooks into a bunch of vectors, and then train an SVM or whatever. Yeah. So today plan is and then Thursday, Friday are the midterms. So as we mentioned, you can take either exam either day. So if you want to bang it all out Thursday, cool. If you want to split it up, cool. If you want to procrastinate until Friday, seems weird, but cool. So I think Varun and I think are planning to just have kind of class both days at the normal time. And as we were proposing this, we got some pushback, concerns about academic dishonesty and that kind of stuff. I stood up for you all and said, no, these students would never do anything like that, so please don't make me look like a chump. And I think you all know that you're not really helping yourself or anybody else by telling people what the questions are ahead of time or anything like that. All right, cool. Test is my standard test. Probably most people hopefully will finish in an hour to hour and a half. That's kind of my target. Yeah. So Any general scheduling kind of questions before we just kind of go through what we've seen so far? All right, cool. So the first thing we talked about was, well, we talked about Python and pandas and that stuff. I'm not going to ask you to write code on the exam because, you know, I couldn't do it. So that's the kind of thing you just need access to documentation. You need to be able to run it and look at error messages. So yeah, if you don't know what the name of the parameter to change the line thickness in your plots is, that's fine. So the first kind of core concept we talked about was statistics. So we talked about two families of statistics. We talked about the descriptive statistics and the inferential statistics. What are descriptive statistics? What are they used for?
Just understanding the data set. What are the patterns in it?
How is it different? How does it work differently from, say, visualization?
Visualization part of it.
It could include some of that information. I would say the key difference is visualization can try to show a lot more of the data set, whereas the descriptive statistics are really a summary, right? And they tend to be a pretty short summary. Right? So what are some of the descriptive statistics that we've put down? Max, min, mean, median, standard deviation, variance, quartiles, so other order statistics, the correlation, all those sorts of things. So again, they can summarize the data for us, give us just an overview of what it looks like. Right? So you should know what the basic descriptive statistics are and what they mean. They don't tell us everything we need to know. So remember we saw the Anscombe's quartet, which was the 4 data sets that had the same mean, standard deviation, correlation, and maybe even the same like linear regression fits, and they were all totally different. Right? So the descriptive statistics don't tell us everything. Right? And then the inferential statistics, what was that about? Kind of a different beast.
Predictions. I don't know how to say it.
Yeah, it was related to predictions. About understanding our data. We're taking a different view of what our data is. And so when we're talking about the inferential statistics, like the data that we collected, like what did we think it was? We thought of our data as a sample from some larger population, right? And our hope was that that larger population can be modeled with like a simple probability distribution. Right? So we get a bunch of data, and maybe we assume that it's a sample of a population that has a normal distribution with some mean and some standard deviation. So yeah, the inferential statistics, we assume our data is some samples from a distribution, right? And the things we can do is we can try to describe what that distribution is, right? So if I assume that my population is Gaussian, right, I can compute my sample mean and sample standard deviation, and estimate what I think the distribution looks like. Right? And then kind of the next level was to hypothesize what that distribution looked like. Okay, well, I think I have a normal distribution with the mean age of 20 people, 20 years old, my population, and then we can decide whether or not our sample is likely to have come from that kind of distribution or not. And so the kind of the inferential statistics led into the hypothesis testing. Say, okay, could our data really have come from, is it likely that our data came from this distribution that I think I'm working with? So what were the various probability distributions that we saw? We saw Gaussian. This is like our go-to. This is a discrete or a continuous distribution. It's continuous, right? I sample this, I get any value. This is also a little bit weird because it has infinite support, right? I could get any number. If I picked a sample from a Gaussian distribution, I could get any number from negative infinity to a positive infinity, right? Pretty low probability of getting something really far away, but non-zero. Okay, so Gaussian was a good one. What other distributions did we talk about? Bernoulli? What does the Bernoulli distribution represent? This is the coin flip. And so basically we have probability P, the probability of heads. If we say heads is 1, right, this has a mean of P. Right, so this is very simple. Is this one a discrete or a continuous distribution? This is discrete, right? I get heads or tails. And if I was going to draw a picture like this for my Bernoulli distribution, what would it look like? We're going to try to graph it. Yeah, it's kind of, the box might be kind of misleading. Right? So if I have I really only have 2 points here. Right? I have the probability P of getting 1 and a probability 1 minus P of getting 0. Right? The box kind of implies that there's an area there, but it's not really. Okay. What is this curve called here? Or this function here that I've graphed? So this one is the PVF, probability density function. Okay. And what about this one over here? Close, not quite the same. The PMF. Anybody remember what the M stands for? Mass. So if you kind of think about this in physical terms, right, we have this continuum thing, right? We're talking about the ocean, we can talk about like the density of water, right? And to like get the mass, we kind of have to look at a region of water. Whereas here, if we're talking about sand, maybe we're talking about the mass of an individual grain or something. Right? So with the discrete things, you know, we have the mass of those things. Here we have the density that we have to kind of look at a volume or an area to turn into a mass. So what is the probability mass function is pretty easy to interpret. It tells us the probability of getting a particular outcome. Right? Nice and straightforward. What does the probability density function tell us? But does it tell me, if I look at the PDF here, does it tell me the probability of sampling a value at this point? Yeah. So it tells me the relative probabilities between various points. Right. What is the probability of sampling this point right there? It's 0. Right. The probability of getting any particular value is 0 because there's an infinite number of possible values, so the probability of getting any one exactly is 0. So the PDF on its own is not super useful. All right, how do we make use out of it? Yeah, so we'll get to the CDF in a second. It's kind of a helpful, gets us there. Yeah, so instead I look at the probability of picking a point within a range. Okay. Right. And so if you remember your calculus, what we're doing here is we're taking the integral of this, right, and we're looking at the area under this curve, and the area tells me the probability of being within a range. So, another way of thinking about the probability of any particular point being 0 is like the width of that range is 0, so 0 times whatever is going to give me 0 area. So, so the probability density function, right? I can integrate over a chunk, and that tells me the probability of sampling something in that range. So these integrals can be tricky to compute. So we'd like to come up with one table of values that we can use for any particular range, and that is how we came up with the CDF, the continuous, or sorry, the wrong keyword, cumulative. I think it's distribution function. Okay. And does anybody remember what this tells us? If I look at the CDF at a value y, it tells me the probability of sampling and getting an x that is less than that y. So the CDF is basically the area from -infinity up to some point here. And so CDF at this point would be basically that area. And that tells me the probability that if I sample, I'll get something left of this point. And we saw that the CDF can actually help me compute stuff like this. How do we use the CDF to? We just subtract. So we just evaluated the two sides and subtract. Okay, so the difference in the CDFs will give us the area in between. Okay. So if we want to know the probability of a particular event happening, right, we can either look at the PEMF, or the to get the probability of a single event happening. The CDF can be helpful if we want to know about a range, because we can find the CDF of the endpoints and subtract them. I think the CDF has the same name for the discrete ones. So we can use the same nomenclature once we start talking about ranges. Any questions about how we can use these probability distributions? If I sampled a bunch of points out of these and drew a histogram, what would I expect it to look like? So I would expect the histogram to look like the PDF, right? Because it tells me kind of the relative relative probabilities of of sampling different values. Right? So if I sample a bunch of points and draw a histogram, it'll converge to look exactly like the PDF if I take enough samples. Cool. All right. So that's two of the probability distributions we talked about. So the Gaussian and the Bernoulli. There was one that was pretty closely related to the Bernoulli. Binomial. And this had one extra parameter. So does anybody remember how the binomial is related to the Bernoulli?
It's going to do a certain number of experiments.
So I take a Bernoulli coin and I flip it n times. So n is just the number of times I flipped a coin, right? And what does the binomial distribution tell us? So, the binomial of p and an x, right? This is the probability of getting x heads in n coin flips. So if I were to plot is this a discrete or a continuous distribution? Discrete, right? I can only get whole numbers of coin flips, right? If I were to plot the binomial distribution, right? At each point, it tells me the probability of getting that many heads out of n coin flips. So the binomial is just basically the sum of a bunch of Bernoulli random variables. We talked about, I think, two other distributions, one more so than the other. So we talked about the Poisson distribution. Yeah, does anybody remember what that one told us? I always think about home runs in this one. It is related to time.
Random events.
Yeah, so if I have random events that occur at some rate, Poisson distribution tells me the probability of seeing a particular number. So the example I like is home runs are hit at a rate of 0.3 home runs per inning on average. So what is the probability that I will see 3 home runs in an inning? So Poisson takes basically a rate, says how often these things are, right? And it tells me the probability of seeing say n events that occur at that rate. Okay. So if on average there's 0.3 home runs per inning, right? It's going to have a maximum at at 0 or 1 probably, right? I expect to not see home runs or to see 1, right? The probability of seeing 100 home runs in an inning is not going to be 0, but it'll be very, very small. Is this a discrete or a continuous distribution? This is also discrete, right? Because I'm looking at the probability of seeing 10 home runs or 3 home runs or whatever. This one's a little bit tricky because the rate is a continuous thing, right? I don't have to, the rate of home runs can be, you know, fractional, but I can't see half of a home run. A ground rule double, like I said, you can't see a third of a home run. And then the last distribution that we saw just kind of briefly is the student's T distribution. I remember that. We saw it in hypothesis testing. Basically, it's a fat Gaussian. So it's a Gaussian with more weight in the tails. When we're less sort of sure about our sample, we think maybe the things might not be independent or the size is too small. We want to do a hypothesis test where we're being a little bit more conservative. The student's T is just a Gaussian with longer tails. I think we only kind of used that once or twice. So these are our probability distributions and kind of what they model and kind of what we can do with them. Any other questions about probability distributions? Okay. So once we have these, we talked about how we can use them to perform hypothesis tests. Okay. So the idea is basically we form our null hypothesis. This is usually something related to a probability distribution. Okay, so we saw when we were talking about alpha beta testing, our hypothesis was that in our population, people like A and B equally well. Right? Or we saw an example where our hypothesis was the average weight gain of freshmen in college is more than 15 pounds. Right? So we're talking about probability distribution stuff. So there we're talking about the mean of things or the variance of things. Okay? So we have our null hypothesis, right? And what we're trying to do is figure out. So this is usually called a hypothesized probability distribution. Okay. And when we're doing a hypothesis test, what we're asking is if this is really the distribution that the population has, how likely is it that we would get data like the data that we got out? So if hypothesis is true, what is the probability of getting a sample like we got? Okay. So for example, in the freshman 15 one, okay, if the true population has an average of 15-pound weight gain, what is the probability of us seeing a sample where the average student lost weight? Okay. And so the hypothesis testing, we're trying to actually put a number on the probability of this happening. Okay. So usually the way we do that is we compute a test statistic, okay, which we usually, the idea there is we took a bunch of samples, compute this statistic a bunch of times for each sample. We would expect them to come from a certain distribution. So, if our hypothesis is true and we took a bunch of samples and ran the test a bunch of times, we'd expect to see a Gaussian distribution in the test statistics, for example. So usually we can't sample, thousands of times. We sample once, and basically all we can look at is, are we way out in the tails of a distribution we expect, or are we close to the middle? Okay. So Right, so here is my expected test statistic distribution. Right. A lot of the time we expect it to be, come from a Gaussian distribution. Right. If my test statistic is out here, right, it is pretty unlikely that this is the real distribution of the population, right? And I just got a really weird sample. Right? So if I see this, right, probably my hypothesis was wrong, and the real distribution does not look like this. In that case, I can reject the hypothesis I came up with and say it is not true, and I can quantify how confident I am in that belief. If I compute my test statistic and I get a value right there, does that tell me that my hypothesis was true? No, right? Because this distribution would also, if this were the true distribution, it would be totally reasonable for me to get this value from that distribution as well. Right? There's many distributions that could, that it is reasonable to get the test statistic value that I got, right? So really all we can do with this hypothesis testing is see when our hypothesis is way off, right? So over here I can say, it's very unlikely that this hypothesis was true. Okay. So we go through this process. Usually at the end we end up with a p-value. What does the p-value represent?
It's a predetermined value that lets you accept or reject your null hypothesis.
So that would be like my threshold for the p-value. So before I start, I want to pick a threshold value. And then when I get my p-value out, I compare it to this. And what does this p-value actually mean? Yeah, it's related to the tails.
Probability value average through one walk through.
Yeah.
We got, assuming our null hypothesis is true.
So basically, usually, so I could think of it as either the area from here out to infinity. Depending on the test, it might also include basically, if I reflect it out here and go out to infinity this way, right? So depending on how I measure extreme, it could be one-sided or two-sided. But yeah, it's the probability of being, further away from the mean than I am, or than our sample is. So it's basically the area from that point to infinity, maybe times 2. Okay. Right? So that tells us the probability of getting a sample as extreme as the one we got if our null hypothesis is true. Okay. If that is super, super low, right? If the probability of seeing a sample like this is 10 to the minus 5, then, probably I didn't get super, super, super lucky or unlucky. Probably my hypothesis was wrong, right? And I should say that my hypothesis was wrong. Okay. So the p-value tells us the probability of getting data like the data that we saw if the whole null hypothesis was true. If that is very low, then we can conclude that our hypothesis was wrong. So another word we'll see for this threshold value is the significance. Right? Another interpretation of that is basically it's the probability. Our p-value is the probability of us incorrectly rejecting the null hypothesis. So, if there was a 3% chance of us seeing data like this, and we say our null hypothesis is wrong, well, there's a 3% chance that we just did get an unlucky sample and we're making a bad conclusion. Right. So there's a lot of confusing lingo here, but the gist is we have a hypothesis about the distribution of the population, and we're just trying to measure how likely is it, what is the probability of getting something like what we saw, if that is true. Yeah.
Can you talk about where the significance is?
Yeah, so the significance is basically my cutoff that I want to decide ahead of time for whether or not to reject my hypothesis. So I would say, okay, if there was a less than 1% chance of getting data this extreme, I will assume that I wasn't unlucky and my hypothesis was wrong. So like 1% or 5% are kind of typical thresholds. And it's just, where I take that probability that I get my p-value and I turn it into a binary, reject or not. Alright. So I think those were kind of the two trickiest topics that we covered. A lot of math and lingo and stuff. Hopefully, the intuition for what we're actually doing makes sense. Cool. Then we started looking at pretty pictures, talked about visualization. So we talked about just some common plotting techniques. So what are some of the basic plots that we've looked at? Scatter plots, right? That's kind of the most common and a very effective technique. We had more categorical data. What might we use? We had like a mix of categorical and quantitative data. We had like a bar chart. If we're interested in the distribution of things, what tools might we look at? Histogram is a good one. Yeah, box plots. I saw the violin graphs if you wanted to actually draw what the distribution was instead of just looking at the like where the quartiles are. Right. So there's just kind of some of the common visualizations that we've seen. If we look kind of more fundamentally what a visualization is made up of, we kind of have two ingredients to visualization. Let me remember what they were. Two basic elements. So marks and channels. So what's a mark? Yeah, so it's some visual element, and what does it like represent?
Existence of something.
Yeah, it tells you basically the existence of something. So a line or a dot or a circle or whatever else, it tells you like, here's data. Right? It tells you that there is something there. So they could represent an element. It could also represent like a relationship, right? So it could be like an edge in a graph drawing, something like that. But it indicates the presence of some piece of data. Okay. And then what is a channel? So examples would be color, size, and what are they for? Yeah, so quantitative or other features of the data. Okay, so we have the marks tell us about the existence, the channels tell us about the features. Okay. So what was the best channel that we talked about? What's our favorite go-to channel? Color, not that great actually. Size is better. Distance close.
Position.
Position was our best.
Where it is.
Is our best one, right? Scatter plot, right? The channel that we're using there most is position. Right? So if we can use the position channel for our most important features of the data, we should do that. There's times where we couldn't, right? So if the data has some sort of position associated with it, and we can't really use the position for like intensity of some feature. Right? So if we're looking at like election results, right? We kind of have to use the position for, position. Right? But that's our best channel. The other ones we talked about, size works great for 1D stuff, less well for 2D stuff, pretty poorly for 3D stuff. Right? Color was a tricky thing. What were some things we had to worry about with color? Color blindness.
Misconveying information.
Yeah, so the perception of color is tricky, right? So like a rainbow scale, even if everything has the same like computational brightness, right? If we have like sum up the RGB components and they all have like the same sum, the perceived brightness is going to change, right? Yellow is brighter than blue, just in our perception. So we're going to introduce stuff that will be perceived as extra information that we're actually not really trying to convey. Right? So we saw that we had a color map, right? We wanted to pick values that didn't have, brightness peaks in the middle. The rainbow color map is usually not very good for quantitative data. What was the rainbow color map better at? For continuous data, it's not so great. Yeah, so it's great for categorical data, right? We can distinguish colors. We can distinguish, like 8 or 10 colors pretty well, right? So it's easier for us to see like these things are different. Okay. So color can be great for that. So that's hue is the like color part. We can use different hues for identifying things. So it's really good. We talked about symbols. Symbols can be great. We're easy or good at telling those apart. Also good for categorical data. Very bad for data that has any sort of ranking associated with it. Same with color. Like, is green bigger than blue? Not really. Right? It doesn't make sense. Good for differentiating categories, but not so great for imposing an ordering. Right. So yeah, we use the marks to indicate the presence of our data. So some marks would be, points, edges, regions, all that sort of stuff, right? And then our channels tell us about the relative values or the values of the features of our data. So yeah. So those are the two kind of foundations of visualization. Other questions about visualization stuff? All right, cool. Next topic we talked about was linear regression, or least squares regression. What's the key idea there? We have some. So first up, is this a supervised or an unsupervised method? Supervised, and what makes it supervised? So we're basically trying to fit some function to our data, and for our training data, right, we know what all the y's and the x's are, so we can kind of measure how good we're doing as we go. So for ordinary least squares, where does the term least squares come from?
Taking the distance of each point, and then squaring it, and trying to get the smallest value.
So we're measuring the error by looking at the squared difference between the actual data point and our prediction of the input. And we're trying to minimize this over all the data. And so that's the least part is we're minimizing this error, and the squared part is it's the squared error. Okay. All right, so that's how we measure how good of a fit any of these models are, is we look at the least squares error, right? So we pick the one that has the minimum. Okay. So we can compute this really efficiently when the models that we fit have a particular form. So what's like the limitation on the models that we can fit with ordinary least squares?
Yeah, be linear.
Yes, but linear in a specific way. Let's look at some models that I might come up with. This one okay? Could I find a beta 0 that minimizes the least squares error? Sure. What do you expect that would be?
Straight line.
Straight, yeah, constant. At what value? If you had to guess. Probably not 0. Yeah, probably the mean. Right? So this is just going to be a flat line through the mean. We can solve. It's not a great model, but we can solve for it. It's fine. Cool. Is this okay? Cool. This was the first example we looked at, right? We can solve for beta 0 and beta 1. There's a nice closed form solution for it. Cool. Right. This is a line. Right. What is this? What shape are we going to make with this? There's no squares here. So the x1, x2, x3 are just input features. So again, there's no powers here, so it's still like a straight thing. It's not quite a line anymore. There's a line now, it's like a 3D thing. So this is a plane, right? It's a flat plane. Right? If I throw my x3 in here, throw it up here. This is called a hyperplane. Right? It's just a plane in more than 3 dimensions. Cool. All these are good so far. Let me throw in another term. Is this okay? I think to the examples we did we do anything like this? We actually did something like this when we were talking about the advertising data sets. We had a term that was like TV times radio or something. Right? And that's actually totally fine. Okay. This is not really a linear function anymore. It's not linear generally, but it is linear in terms of the betas. Okay. So our restriction is that as long as the betas are just multiplying something in front, we can do anything we want. Right? So I can add beta 6, sine of x2 minus x3. That's totally fine. Okay. I can still fit this with least squares. But what I can't do is put my beta anywhere else. Right? So here, if I like have a beta in an exponential term, I can't do that. Right? I can't do something weird. I couldn't like have my betas be multiplied together. That doesn't work. My betas just have to be in front of the terms. But other than that, I can do whatever crazy stuff I want. So those are the functions I can fit, right? And I'm going to get, as long as I follow those rules, I'm going to get the best possible function of that form. I'm going to get the best betas, and I'm going to get them really efficiently, really fast. Okay. So I get this model, I get the betas, and then I get a couple little bits of information that can help me determine whether I have a good model or not. And what are the other pieces of information I get out? Get p-values for my betas. And what else?
Just to clarify really quick too, in the code, that wasn't the coefficient that we got.
It is, yeah, the betas are the coefficients. So we have the p-values for each thing, and we have like one overall summary of our model. The R-squared value. So what did the R-squared value tell us?
How many points we are using in this title?
So it wasn't like a discrete thing, it was more of a continuous thing. What was the range we could get for R-squared? I think it's 0 to 1. I don't think we can ever get negative just because of the way the formula is set up. And because we're always picking the best fit, I don't think it's possible.
Where the correlation is whereas R-squared is 0.
Yes. Right. So the R-squared value tells us basically how much of the variation in our data is explained by the line. And it's a measure of how close our points are to whatever function I fit. So if I get an R-squared of 1, every point is exactly on the line. If I get an R-squared of 0, like it's not even close. Right? So stuff's kind of sprayed all over the place. Right? And then in between, I get closer to the line. Okay. So the R-squared tells you how much of the variation in the data is explained by the model that it came up with. Okay. And what do the p-values tell us?
Try data is relevant to your function.
So it is a measure of basically whether we should include this term or not. Does anyone remember specifically what that p-value, so it's a hypothesis test p-value. Does anybody remember what the hypothesis test is? What the hypothesis is that they're testing? So what is the null hypothesis that p-value corresponds to? Yeah, so the specific hypothesis test is, our hypothesis is this coefficient is 0, right? And we get the p-value associated with the hypothesis test, right? So if we have a small p-value, right, it means it's very likely that the true value of the coefficient is not 0, and it should be included in our model. Right? If we have a big p-value, it means it is reasonable, it's very possible that this coefficient is truly 0, and maybe you shouldn't include it in the model. So the p-value tells you basically the probability that the coefficient is actually 0. Okay. Cool. So that was linear regression. That was the first supervised learning method we looked at. Any other questions on that? And then the next supervised learning problem that we looked at was classification. Okay. So how is classification different from regression?
should add this or that.
Yeah, so it's the type of the output variable, right? So with regression, we had a quantitative output variable, right? Like home sale price or I don't know what else, horsepower, whatever, gas mileage. Whereas with classification, it was a categorical sort of data. So accepted into school or not, or iris species or whatever. Okay, so for classification, we had a quantitative output variable. Okay. The first method we looked at was logistic regression. What did that look like? That's kind of the shape. That's the S curve, the logistic function curve, right? And basically what we're doing is we're doing a least squares thing, and then we're smushing that into the S shape. Okay. And the nice thing about that is the S shape has a minimum of 0 and maximum of 1. So how can we interpret the output of our logistic function output? So we can look at 0.5 below, 0.5 and above, and how can we interpret what that value means? We can think of it as a probability. So with the least squares regression, right, we can still put a cutoff line in there, but we're going to get values that range from negative infinity to positive infinity probably, right? With the sigmoid, with the logistic function smushing it, right, we can think about probability of being in a particular class. Okay. So when we set the probability to 0.5, we get the decision boundary, right? And what was the shape of that going to look like? It's always going to be a line or a plane or whatever. And the reason is because we basically take a line or a plane and then we just smush it. So we take something straight and then we smush it with the curve, right? And so there's the line where we would cross on the plate on the straight thing is also the line where we would cross on the smushed curve. Okay, so that was logistic regression. We talked about K and N for classification. So how did that work? Conceptually, it's pretty easy. We just look at what's nearby and let them vote. Okay. What knob do we have there? We have our knob K. If I set K equal to 1, what do we expect to happen?
Okay, I mean, you just have one neighbor, so you all count. Everything's the same.
No,
not like-
one would be the same.
Neighbor.
I do really, really good on the training set because
Yeah,
for the training set, I'm just looking up what the right answer is. Cool.
and bad.
And then for my testing set, what would happen? Do pretty lower accuracy. And what do we call that when I have much higher training accuracy than testing accuracy? Overfitting, right? If K is 1, I overfit the data. I'm going to have a really noisy decision boundary, right? Great accuracy on my training set, terrible accuracy on my testing set. Okay. If I have K of infinity, what's going to happen? A really big K. Does it matter where I query? No, right? I'm just going to do majority rules over the whole data set, right? So my decision boundary won't exist, and I'll just pick one value for everywhere. Okay. How would we classify, or how would we describe what happened there? Underfitting, right? So if my K is too big, I'm underfitting the data. I can't find a good decision boundary. So those are the two extremes. We looked at a bunch of different data structures for doing that. The next classifier we looked at was decision trees. Okay. So using a decision tree is pretty straightforward. You just follow the branches down. Constructing one, we basically just looked for the best split we could find and then split it up. What were some of the knobs we had to tune with decision trees? height, we could set a max height. And there's one other knob we used. The minimum split size. Right? So if we had a node that was, had 2 elements in it, we don't need to split that. Right? Not that helpful. Why did we want those knobs? What did they help us with? Overfitting, right? So decision trees have a strong tendency to overfit. Those knobs can help us reduce it a little bit. And we also talked about a couple other techniques for avoiding overfitting with decision trees.
Multiple decision trees?
Yeah, so we trained a bunch of decision trees. There's actually 2 kind of strategies we saw for that. One was called bagging, and I remember that one, what we did there. So we just made a whole bunch of new data sets by sampling from our original data set, trained a bunch of trees, and then let them vote. So we duplicated our data a bunch of times to make that happen. And the other strategy was called the random forest. And what did we do there?
Randomly select and then make decision trees and then look at you can take different splits, the splits are different.
Yeah, so for the random forest, we restricted which features we could use to split. So each time we had to split, we said, okay, randomly, these are the ones you can look at, right? And that's going to give us decision trees that have more variation in them, and so the voting is going to hopefully be more beneficial. Cool. And then we saw there we could use cross-validation to if we don't cross-validation let us make a training and testing data set so that we could see if we were overfitting or not. Yeah.
I was just curious, can you use cross-validation for the actual, the half that you, once you split it into testing and then the other half?
Mm-hmm.
When you do it, do you use all of it, or do you only ever use one half for testing and then the other half?
So usually, if you contaminate your training data with your test data, you're going to overfit. So if that information gets used to train it, you're not really, your test data is no longer really test data.
Does it ever happen where you split your data in a really bad way?
It could happen, yeah. We split it randomly. You might, so for the, we talked about the k-fold cross-validation. We split it, k different ways, and kind of hoped that that would sort of average out if we got a particularly bad split. So yeah, one thing you do is repeat it multiple times, or like we talked about in systems, for the paging stuff, the solution is get more RAM. The solution here is get more data. The unsatisfying, but ultimately most effective solution, just get more data. So those are the classification techniques we saw. So logistic regression, KNN, oops, I left one out. Which one did I leave out? So is that classification? Nope. The support vector machines, the SVMs I left out. What knobs do we have there? Really, we had kind of 2 knobs to turn. One was a categorical knob, and one was a quantitative knob. So we think back to where the SVMs came from. They started out by basically trying to stick a slab in between are the two halves of our data, and we had one knob for the type of slab that we fit. Yeah, so we had this parameter C, which is like the cost or the budget, right? And a bigger C let the slab be thicker, okay? Which means that we included more data, right? And a smaller C meant the slab was thinner, which meant that we were looking at fewer points kind of near the boundary. Okay. So that was one knob. And then the second knob was basically, fitting a slab is what we basically did for logistic regression, right? Where we had like a straight line decision plane. So the weird thing we did with SVMs was we added this kernel function that let us do weird space warping, whatever. And so our other knob is the choice of the kernel function that we can pick. Right? So the one we saw a lot was the exponential, so it was like e to the negative gamma, like distance squared or something. But we can pick different kernel functions, and that'll also give us different ways of warping the space. Yeah, but kind of the major, so those are the two knobs. So we have our budget, which is how thick the slab is, how many points are we really looking at as we try to optimize our slab, and then the other is how we do the dot products. Cool. All right, and then we talked about clustering. So what's the difference between clustering and classification? Related to kids getting in trouble. Supervision, right? So clustering is unsupervised, right? And what did it mean that it was unsupervised?
The ideal, the goal.
Yeah, we don't have any ground truth labels for this data. Right? We don't know that the points are in a particular class ahead of time. We just know that there's points, and we think that maybe there's grouping. Okay? And so we're just trying to figure out, okay, like what groups are present in this data. So we talked about k-means clustering, right, where we just basically throw down k points, and we optimize to try to get those points in the best possible positions so that the clusters are kind of as compact as possible. Okay. What was the hard part about using k-means clustering? Picking k, right? So how many clusters should there be? And we talked about 2 ways of dealing with that.
The elbow.
So we talked about the elbow analysis or the elbow method. Right? So we looked at we look at the compactness of the clusters as we increase k. They're going to get better and better and better. Right? If k equals n, then each cluster is as small as it could possibly be. Right? The points are as close to their cluster centers as they could possibly be, but we're going to hit diminishing returns. Right? So if we look at that graph, as we increase k, we're going to kind of decrease the cluster distance, and then at some point, hopefully, we'll see kind of the kink where, like, okay, we hit the natural number of clusters, adding more doesn't really make things compact faster. So we took this clustering, which could be like an ND kind of thing, right? And we tried to turn it into like a 2D picture we could look at and see, like, okay, distance from points to clusters versus k, and then we could look at that visually. The other technique was silhouette analysis. Right, the silhouette score, so let me remember what that depended on. So it's basically related to the distance from a point to the neighbors in its own cluster versus the distance from points into a nearby cluster. And we computed like a score based on that, right? So if we have good clustering, right, we're going to be very close to the points in our own cluster and much further away from points on the other clusters. And so we could use the silhouettes to kind of score how we're doing. We saw the silhouette graphs. For good clustering, right? Almost all of the points are, have a very high silhouette score, and then the ones at the boundary are not so good. But we kind of saw what the silhouettes looked like when we had too many clusters or too few clusters. Okay. And then the last technique we talked about was the hierarchical clustering, and we looked at the bottom-up version, which is called agglomerative clustering. What was the key idea there? So we start with every point in its own cluster, and then how do we get less than n clusters? So we just merge clusters until we have a single cluster at the top. Okay. Right, so we talked about a few different ways we could measure the distance between clusters. So first off, there's a bunch of different ways you can measure the distance between points. And then measuring the similarity between clusters, you could either look at the average or the centroid or the closest or the farthest points of the cluster. Or you have this Ward's one, which is like which clusters would be best to merge. If you kind of look at what happens after you merge them, which one's the best. And then we got a picture out of this at the end. What was that picture called? Called the dendrogram, right? It's just a picture of all the clusters where they're joined. Okay. What does the x coordinate of our points tell us? The points or clusters tell us?
How many clusters?
That's a trick question. Nothing, right? The x position tells us basically nothing. It's the aesthetic, right? But what does the y position tell us? Yeah. So it tells us about the relationship between the clusters, specifically. Tells us the distance between them, right? So if you merge clusters at the bottom, right, they're very similar. If you merge them at the top, they're not that similar, right? So we can use that to kind of pick k clusters if we want. We can kind of go down until where everything is pretty similar. All right, cool. So that's pretty whirlwind. I would, to study, I would say, try to answer the questions in the midterm warm-up stuff. Look through the notes. It helps me a lot to think about the examples we did for each of these, right? When we're thinking about the linear model, like the least squares, or think about what we did with the cars, right? Okay, what are the terms that we had there? Like, what worked, what didn't. So, any other questions?
I have a question about the linkage criterion.
Mm-hmm. So the linkage criterion is just how we measure the distance between clusters. So it's just a word for inter-cluster distance. Cool. So tomorrow, we'll talk about NLP just a little bit. There's going to be one exam question on it, but we're not going to go into a ton of depth on it because there's basically just too much you can do with it. All right. Cool. I will see you tomorrow.